Hello, thanks for being here. My name is Chauncey Fontenot, and today we're talking about forensic identification, specifically how the legal system tries to connect invisible, accidental traces left at a scene to a specific individual. We've all seen crime shows where a computer flashes a green light and instantly solves the case. But in reality, forensics is a mix of hard science and human psychology. Today, we're going to look at how we turn daily, random contacts into our courtroom proof. To understand why this matters, we have to look at a basic rule of simply existing. Every interaction leaves a mark. It's an invisible signature. Every time you grab a door handle or type on a keyboard, you drop physical and biological clues. Forensic identification is just the process of catching those random traces and translating them into facts. When the system gets it right, it secures justice. But when the human element fails, it carries a real risk of a wrongful conviction. Here's our roadmap for today, broken down into three pillars. First, fingerprint analysis, moving past basic patterns to look at the testing protocols experts use. Second, forensic odontology, how dental data is mapped and tracked. And third, touch DNA analysis, how a tiny invisible cluster of skin cells gets turned into a full genetic profile. Let's start with our first pillar and probably the most classic tool in the handbook, the fingerprint. The biology here relies on friction ridges. These are the tiny raised patterns on your fingerprints. They form before you're born and stay exactly the same your entire life. Because of the natural oils and sweat on our skin, whenever we touch something, we leave behind a stamp of those ridges, usually loops, whorls, or arches. In forensics, we call these latent prints, meaning they're hidden from the naked eye until we dust or chemically treat them. So, how do you go from a faint smudge to a definitive match? Analysts follow a four-step pipeline called the ACE-V protocol. A stands for analysis, checking if the crime scene print is clear enough to use. C is for comparison, putting it side by side with the suspect's print to look at the tiny details. E is evaluation, making the call if it's a match, an exclusion, or inconclusive. Finally, V is verification. A second examiner runs the entire process again completely blind. This human double check is what keeps the conclusion objective. When we look at how this applies in the real world, we have to talk about the human factor. Even though ridge patterns are unique biology, identifying them is a human process. As highlighted by Moringa and Maludazi in the 2026 case, data shows that things like evidence mismanagement or a lack of specialized training are the primary causes of failure when trying to secure a conviction. Examiners are rarely handed perfect prints. They are interpreting incomplete, smudged data under intense pressure. The strength of the evidence lies clearly in the precision of the investigator, not just the science itself. This brings us to a core psychological framework, signal detection theory. Because fingerprint analysis relies on human judgment under pressure, the examiner's brain is constantly trying to separate a true forensic signal from messy background noise. Think about professional wrestling. When you're a kid, you think it's 100% real athletic competition. Then you grow up and realize there's an entire scripted storyline happening behind the scenes. Forensic analysis can be the same way. When we want to believe it's pure science, or we want to believe it's pure science, but cognitive and contextual biases act like a script behind the scenes. If you look at this matrix, shifts in judgment change real world outcomes. A hit correctly catches a criminal, and a correct rejection clears an innocent person. But if an examiner is fed outside case details, like being told a suspect already confessed, it subconsciously lowers their threshold. This bias can trick them into declaring a match on a bad print, creating a false alarm and a wrongful conviction. On the flip side, if their threshold is too high, they might commit a miss, failing to identify a true match and letting a perpetrator walk free. Let's pivot now from skin ridges to something much more durable, human teeth. This brings us to forensic odontology. Forensic dentistry works because teeth are incredibly tough. They are the hardest, most resilient substances in the human body. Soft tissues decay, and even blood or skin DNA samples can completely break down under extreme conditions. But teeth can survive intense fires, severe trauma, and advanced decomposition. Because everyone has a totally unique combination of alignments, gap sizes, and fillings, your mouth acts as an unalterable biological record of who you are. The workflow to identify remains through dentistry is highly meticulous. It starts with post-mortem profiling, examining the deceased and mapping out the mouth using photos and digital x-rays to code every single tooth. Then, investigators track down the missing person's past dental clinics to gather their ante-mortem data. Finally, the specialist overlays both sets of data onto a standardized chart called an odontogram. They check every filling shape and root angle. If the two charts match perfectly with zero unexplainable differences, you have a positive identification. So when does this tool become the primary line of defense? As documented in the literature by Miller, 2024, as well as Wood and Gardner, 2023, we rely heavily on dental identification during disaster victim identification, or DVI. In major aviation accidents, explosions, or sudden natural disasters, traditional physical features can be completely obliterated, and standard DNA sources are often highly compromised. In these intense mass casualty scenarios, forensic dental records step in as the primary method to restore names to remains. Expanding on that DVI framework, why is this method globally recognized as a gold standard? First, even when a disaster causes severe biological degradation that breaks down raw DNA strands, dental structures retain 100% identification accuracy. Because of this reliability, forensic experts emphasize that establishing international standardization for dental charts is vital for global justice and safety coordination. Furthermore, on an operational level, dental identification serves as a rapid, highly cost-effective partner to modern laboratory DNA sequencing, allowing investigators to clear mass casualty files efficiently without sacrificing scientific precision. However, drawing directly from the research of Monica and Gorza 2019, we have to draw a hard, bright line between two completely different applications within this field. On one side, you have the highly objective, universally trusted practice of identifying victims through stable, pre-death dental records, but on the flip side sits bite mark pattern analysis on human skin. This practice is deeply controversial and is increasingly viewed as junk science in the 21st century. Human skin is elastic, it stretches, swells, and heals, making it a terrible shifting canvas. Declaring a match between a skin bruise and a suspect's teeth is highly subjective, which is why modern academic training is actively backing away from it to prioritize data-driven dental profiling. Now let's leave the visible world behind and zoom all the way down to the molecular level for our third pillar, touch DNA. Touch DNA targets the invisible skin cells that we naturally shed every single day just by interacting with our environment. Every time our skin brushes against an object, we leave behind thousands of these invisible cellular traces. What makes this technique a game changer is its hypersensitivity. Modern laboratories don't need a massive bodily fluid sample anymore. They can extract a full, courtroom-ready genetic profile from just a tiny cluster of left-behind cells. So how does this microscopic trace actually solve crimes in the field? Based on the empirical work of Udianto and his team, Everyday personal belongings like mobile phones and watches are excellent sources for touch DNA because they are handled constantly by their owners. The investigative process follows three core stages. First is swabbing, where the target object is carefully wiped down to gather those microscopic skin cells. Second is CODIS analysis, where laboratories target highly specific regions across standard genetic locations to build a distinct profile. This leads directly to the match, providing a statistical identity check that is nearly 100% accurate when presented in a court of law. To go from that investigative swab to a data readout, the sample goes through a strict three-step molecular pipeline inside the lab. First is cell lysis and extraction. The lab treats the swab with specialized enzymes like proteinase K to break down cell membranes, isolating the raw DNA while washing away dirt and oils. Second, because touch samples are so scarce, they undergo PCR amplification. The DNA is placed in a thermal cycler that acts like a molecular copy machine, replicating target markers millions of times in a few hours. Finally, capillary electrophoresis pushes the fragments through a microscopic tube using an electrical current. Shorter fragments sprint through faster than the longer ones, and a laser reads fluorescent tags to output a digital graph. When interpreting that graph, scientists are targeting short tandem repeats, or STRs, regions of our DNA that repeat in lengths that vary immensely between individuals. Following national forensic standards, labs look at specific locations called CODIS loci, focusing on markers like TH01, TPOX, and CF1PO. By mapping the exact repeat count across all these standardized locations at the same time, the mathematical probabilities become astronomical. The odds of two unrelated people accidentally sharing the exact same multilocus profile are literally billions to one. That is where the gold standard certainty of DNA evidence comes from. But science is only good as the real world allows it to be, and not all touches leave behind the same quality of evidence. Pulling from the data by Ostajic and Wurmbach 2017, biological recovery depends heavily on three core environmental conditions. First is surface type. Hard, smooth surfaces like glass and plastic yield a very high success rate because they preserve the cells cleanly. On the other end, metal objects like coins have a moderate to low success rate because certain metals oxidize, breaking down the cells. Second is biology. Gripping an item with your non-dominant hand can surprisingly leave behind a slightly higher skin cell yield due to increased friction. And third is timing. On an ideal, protected surface, these microscopic profiles can remain stable and retrievable for up to 40 days before completely degrading. This data proves that a touch DNA profile isn't a guarantee. Because it relies on these strict environmental and biological thresholds evaluated in studies like Ostajic and Wurmbach, an investigator must evaluate the background context of a piece of evidence immediately. Knowing whether an item sat outside on a porous surface or was heavily handled determines whether a sample is worth running through a costly molecular pipeline or if it's already lost to degradation. If we bring all three pillars together onto a single matrix, the big picture becomes clear. Fingerprints are ideal for tracking presence at a scene via surface contacts, but the process is vulnerable to human cognitive bias. Forensic odontology offers unmatched biological durability for severe disaster scenarios, but becomes highly subjective when misapplied to bite marks on skin. And touch DNA gives us extreme sensitivity for handling crimes involving weapons or daily items, but that sensitivity makes it fragile and highly vulnerable to secondary transfer. This means that your cells could end up on an item that you've never touched before. To conclude, true forensic identification isn't just about finding a trace at a crime scene. It requires an ongoing awareness of both hard science protocols and human psychological blind spots. From the visual checks of the ACE-V framework to the chemical steps of PCR amplification, The integrity of our justice system depends on holding human investigators to strict, objective standards. These advanced technologies don't exist to replace human judgment, they exist to inform it. Managing that intersection carefully is our ultimate path to a fair and just legal system. And these are my APA empirical sources. Thank you.